Okay, so let's start. So today we will talk about scheduling. So the scheduler is the part of the real-time operating system that is responsible for deciding when and which process to throw in and out of from the processor to actually to let a certain task execute or not. We have previously discussed that there are different strategies that can be done. We talked about that each task will have a priority. And in a real-time operating system, that priority is used to, at every point in time, decide which task to run. And this is based on the principle that the operating system will keep a queue of tasks that are ready to execute, so they want to execute, and this queue is then sorted by the priority. So at every point in time it will choose the task with the highest priority and let it execute. And if at some point in time a new task becomes ready, for example, that task might have been blocked on a timer, so suddenly the timer will expire, and then the task will move from block to running, and then the real-time operating system will then, if this new task has higher priority than the currently executing task, it will throw the currently executing task out and bring in the new task with a higher priority. And this is called the preemption. This is called preemption when this is done. And then there will be a context switch taking place. So the context switch is when you change all the registers and the program counter and everything from one task to another. So what we describe now is when you have the priorities when they are static, but they can also be dynamic, as we will see later today. And you can have, instead of having priorities, you can have deadlines that you would like to meet. So we will look into that. But we will start with something simpler. So in some cases you can actually do without a real-time operating system. So if all the tasks are known beforehand, you know when they would like to execute, you could try to generate something that is called the cyclic executive. So if you use this, you don't really have tasks in the normal sense that we have talked about before. Instead, you can think about each task as being a procedure that is executed by the cyclic executive at different points in time. So we have something called the minor cycles and the major cycles. So I think this is best explained by an example. So in this case we have 5 different processes or tasks, and you can see the period time here. So that means that this task A is executed every 25 milliseconds, or whatever the unit is, and 50 and 100. And every task also has some computation time. So this is an estimate of, or a worst case estimate of how much time it will take to finish every execution in every period of this task. So in this case we see that the periods here, they are multiple of this period. And also, 100 is a multiple of 25 as well. So in this case, it's possible to try to do this static scheduling. But we can notice here, if we try to, for example, in the first period, if we try now to execute process A and process B. That will in total take 18 time units. And then if you add C and D, it will be another 9. So that means that it will be 27 time units. So you can't execute A, B, C, D in the same period, right? Because you have to execute A again after 25 milliseconds, and it will take 27 milliseconds to execute all of them. So you have to split up these longer tasks, so C, D, and E, in different periods. So, and how to do this is actually an optimization problem that you can formulate. We will not look into that, but it is possible. So here is one way to do it. So let's say now we wait for an interrupt here. So this means that we will get an interrupt every 25 milliseconds. So the first time we execute A, B, and C. So that will be 10 plus 8 plus 5. So it will take 23 milliseconds, which is less than 25. So then we can wait for a new interrupt after 25 milliseconds. And then we can execute A, B, D, and E. So it will be 10 plus 8 plus 4 plus 2. So 24. And then we do A, B, and C. So it will be 23, I believe. And then we have A, B, and D. 18, so 22. So, and then when we have gone through all this, we loop and do this over and over again, right? So it means that we will execute after every interrupt, we will execute both process A and B, as you see here, A, B, A, B, A, B, A, B. We will execute, so we have 4 minor cycles here, as they are called, and this is the major cycle, the whole thing. So in every minor cycle, we will execute one of C and D. And then in this case, so in one of these 4 minor cycles, we will also execute E. So this is calculated statically. So this is beforehand you start up everything. So before you actually do your compilation of your program. So for this to work, you need to know all the processes and the periods and an estimate of the worst case execution time. But if you do that, you can generate this. And then you can have multiple tasks executing, but you don't need a fancy scheduler. So this is basically the scheduler. So it's just following, going through all of this. And this will simplify things a lot, because this program will execute, so this major cycle will repeat itself. So after it has gone through all the 4 minor cycles, it will repeat and do all over again what it did just before. So this is very deterministic. It will behave in the same way every time. So this is different from when we have this more fancy scheduler that is based on the priorities. Because the advantage with this fancy scheduler is, of course, that you can dynamically start new tasks. So while executing, you can have one task starting another task, and then it will just be, with a certain priority, it will just be integrated in this policy that is implemented by the scheduler, and everything will continue to work. But on the other hand, you can have these strange behaviors as we discussed about last time, priority invariance, and you need priority inheritance and so forth. But with this approach, you know that This is how it will behave. And there is another thing. You will not have preemption here. So after you have started a task here, it will continue to execute until it's done. Okay, so this is also an advantage. Think about, we introduced semaphores and locks, for example, to make sure that you avoided race conditions. But here, you're guaranteed to execute the whole process or the whole task until you're done, right? So you avoid some problems here. So if you have really safety critical systems, then you typically try to avoid having dynamically created tasks. So you would like to know everything beforehand, allocate everything statically, avoid dynamic memory, and do something like this. So it's a simple but quite useful strategy in many situations. So we have a couple of properties here. So we don't really need support for processes from the real-time operating system. So each minor cycle is just a sequence of procedure calls. The procedures can share a common address space, and we avoid the problem with race conditions that we solve with semaphores. But the drawback is that all the processes or tasks that need to be known beforehand, and the periods of the task must be multiple of the minor cycle time. So in this case, the minor cycle time was 25 milliseconds, and all the other periods that we had were multiples of that. So it can be a problem also if you have a very big difference between the short and longer periods. And it's hard to include sporadic activities, that we say, something that should just be executed based on some event or something like that, because it doesn't really fit into this setup. It's also that I mentioned that you can construct an optimization problem to figure out how to do this, but it is what is called an NP-hard problem. So the number of computation steps you need to solve this problem increases exponentially with the number of tasks. But if it's still, with today's algorithms and computers, it's still possible to solve this if you don't have too many different tasks. So for a reasonable number of tasks you can solve this. And if you have a really large or long computation time, you can split it up into fixed size procedures to better deal with it, to have it included in these minor cycles. But the drawback here is, of course, that then if you split up your computations, then you're not guaranteed that each task will do all its computation until it's done. So instead it's split up, so then you need to do the split up at places where you know that you will not have any race problems. We talked about the flexible schedules with different tasks and so on. But what we will spend most time on today is to discuss these or analyze different scheduling algorithms, so that are based on either static or dynamic priority. So we will start with introduce some notation or some words here for different parts of the task execution. So the first term is the release time. So the release time is the first time, and we talk about periodic tasks now, which typically control tasks are. So we should execute periodically. So the release time is the first time when a task is ready to execute the next, at every period. Okay, so now it might be that it doesn't actually start to execute as soon as it becomes ready. So this is where it's being inserted into the ready queue of the scheduler. Because it might be that some other task is executing here. So it might actually start at some later point in time. So this is the start time. And then we have the finish time. This is when the task is done, when it will go and wait for the next period to start. And then typically we have a deadline as well. So the deadline is of course application dependent. So it could be the end of the period, or it could be a tighter deadline as well. And then, as we also discussed, that you might be, while you're executing, there might be some other task with higher priority that becomes ready to execute. So then you might be preempted, and then you're thrown out from the processor, and then you will, at some later point in time, get access to the processor again, and this is the resumption time. So the total time here from the task is ready to execute until it's actually finished, that is called the response time. And the execution time is the total time where you're actually using the processor. So in this case, it's these two times added together. Yeah. Okay, so then we will have some notation here for the examples that we will present. So we will assume that we have n processes or tasks in the system. We assume that each task will have a priority, and we assume here that the higher number will mean a higher priority. It's exactly as it's done in FreeRTOS. So the idle process has the lowest priority, has priority 0, and then all other processes have a higher priority. We will let C denote the worst case computation time. It's also abbreviated WCET of a task. Each task will have a deadline. It's called a D. And we will calculate something called the utilization later, which is basically the percentage of the time that the processor is used for doing computation for the different tasks. So these are the most important. And we will go into two different scheduling principles. We will start with the fixed priority scheduling. It's called FPS, which is what we have talked about so far, that when you write your program, you assign a fixed priority or a static priority to your task. So you will give it a number, 5 or something like that. And this does not change during the execution unless you have priority inheritance enabled or something like that. But basically it's the same priority throughout your execution. And this is what is most widely used. So every real-time operating system, they support this type of execution. So FreeRTOS and commercial ones like QNX and VxWorks, they all work in this way. And basically the scheduler will just follow this priority. So have the processes sorted in the ready queue by their priority, and will always pick the one with the highest priority to execute. So then a problem that you have is, how do you choose the priority? Yeah, and we will see how we can do this, but it's important here to make this that you typically select the priority based on the temporal requirements that you have in your system. So it does not necessarily mean that just because a priority has, or a process has higher priority, that it is more important than some other task. Because the priority will influence when the different tasks are executed. So that's why we say that they are typically derived from the temporal requirements. But this is the standard way. But we will also look into something called the earliest deadline first scheduling. And this is, in some sense, a little bit more natural, because you will not assign priorities to the tasks. Instead, you will assign a deadline. When do we have to be done with the task in every period? So it will post a deadline. And then, basically, the strategy in the earliest deadline first scheduling is to always select the task with the closest deadline for execution. And you can think about this as having dynamic priorities, right? Because when you're close to a deadline, you will have higher priority than if you're far away from a deadline. So that's why you also call this a dynamic priority approach. But we will start with the fixed priority scheduling. We will talk about something called the rate monotonic scheduling. And this is a strategy for how to assign priorities to the different tasks. And it's a very simple strategy, but it has some nice properties. So we will assume that we have n tasks, as I mentioned. Each task will have a period. Each task also has a worst case execution time that we have calculated somehow. And yeah, for this theorem to hold down here, we need to make some assumptions, and basically we assume that all the tasks, they are completely independent. So there are no locks like semaphores between the different tasks. And we need to assume that we have fixed priorities and preemptive scheduling. So some other task will, with higher priority, becomes enabled. It will start to execute. Okay, so what you do in rate monotonic scheduling is that if you have a shorter period, then you will have, that task will have a higher priority. So it's a very simple strategy. Shorter periods, higher priority. And what this will guarantee us is that if there is any priority assignment that yields a feasible schedule. So a feasible schedule here, we now mean a schedule where all the deadlines will be met. Then, if you now assign the priorities in this way, so the smallest period has the highest priority, then this will also yield a feasible schedule. So if there is a way to come up with a feasible schedule, you will get that by this very simple strategy. Shorter periods, higher priority. Right? So it's a very nice result, because it's so extremely simple to compute. And you know that you will not yeah, you will never give up anything by using this strategy. So that's why you say this rate monotonic scheduling is optimal in the sense of feasibility. So we will not go into the proof of this, we just learn the result. So we can just see an example here with 5 different processes, and you have the periods here. So, and you see that they are not multiple of each other. And then basically you go here and you start with the longest period. So process D, you will give that the lowest priority, 1. And then you look for the second longest period, okay, you give it priority 2, and so forth. And also notice that the actual numbers doesn't really mean anything here either. It's just yeah, in which order they come. So this priority will then be used for sorting the processes. So if you have 5 or 1,000 there, it doesn't really matter. It will still be the first one in the queue if it is ready to execute. We talked about deadlines, and if now the deadline is equal to the period, so this is a special case, so you only need to know that you have completed your execution until the end of the period, right? And once again, we assume here that the processes are completely independent, so there are no locks between the processes. Then you have this nice sufficient but not necessary schedulability test criteria. So basically, if we look at this, so U here is the utilization. So, and then we make a summation here over all the tasks. So we start with task 1, and then we basically take the worst case execution time for task 1, divide it by the period of task 1. So what do we get here? Yeah, we get a number between 0 and 1, right? So that we can think about as the percentage of the time that this task is using, task 1 is using the processor. So, and then we do this for every task. And it's obvious if the total number will be above 1, meaning more than 100% is necessary, then we can't meet the deadline. But this is a little bit, yeah, this is sufficient but not necessary schedulability test. So we actually need something stricter than that. So if you have n processes, then we say that this number should be less than, or the utilization should be less than this. So we can compute this for different n. So if you only have one task, okay, so then the utilization needs to be less than 100%. That's obvious. But if we have 2 tasks, then the total utilization needs to be less than 82.8%. And the more tasks we have, the lower this utilization bound will be. But if we let n goes to infinity, this will actually converge to 0.69, so 69%. So what does this mean? It means if you can show that your total utilization for a specific n is less than this bound, then you know that all the deadlines will be met. And since this is sufficient but not necessary criteria, if your utilization happens to be larger than this, you might or you might not meet your deadlines. You don't know. But this is a sufficient criteria. So if the utilization is less than this, you will meet your deadlines under the assumption that there are no locks between the different tasks. And this 0.69 or 69% means that if the total utilization is always less than 69%, then no matter how many tasks you have, you will always meet your deadlines under the assumptions just stated. So we can see an example here. So we have 3 different tasks. And if we look into this formula here, if we put in 3, then we get 78%. So we now know that if the total utilization is less than 78%, then we will meet our deadlines. So in this example, so for task A, the period was 50 time units and the computation time was 12 time units. So task A will use the processor 24% of the time, and 25% for task B, and 33% for task C. So if we add them up now, computing the total utilization U, it would be 82%. So which is larger than 78%, where we are guaranteed to meet our deadlines. So if we now, so if you look at the priority, so it's the lowest priority is to the longest period, and the highest priority is to the shortest period. And if now the scheduler is executing according to these priorities, so they are assigned from the rate monotonic principle. So that means that under the assumption that all the processes are released at time 0, so what will happen? We will start, so the real-time operating system will sort them according to their priority, and it will pick the one with the highest priority for execution. So in this case, the highest priority was task C. So task C will start to execute at time 0. And then it will be done to take 10 time units to complete, so it will be done here. And now it will be blocked, and it will be released again at the start of the next period. So it will be blocked until this time. Right? Okay. So task C is done here, so then it will be the process with the highest priority now among those that are ready to execute. So that will be task B and A. And then task B has higher priority, so it will start to execute now. And it will execute for another 10 time units, and then it will block. And now task A can start to execute. But if we look at task A here, it took 12 time units to complete. Right? So here, 30 time units have elapsed. So now task C is released again, right? And now we will have a preemption because task C is ready to execute. So then the real-time operating system will throw out task A, so it will do a preemption and a context switch, bring in task C, let it execute, and then at this point, when task C is done, task B is unblocked again and will continue to execute. And then at time 50, task C is now the only one that would like to execute, but the deadline here was equal to the period. So when the period for task A was 50, so here task A will miss its deadline. Right? So it's not a feasible schedule here. And the reason was that it was possible to construct this case was because of this. That this, we used the processor 82% of the time, which was larger than 78%. So it would be impossible to construct a schedule like this if the total utilization would be less than 78%. So is this clear? I mean, first how the real-time operating system works, then how to think about the utilization. Remember now, this was under the assumption that the deadline was equal to the period, which it doesn't have to be. But this criteria only holds if the deadline is equal to the period. So it's a special case. But remember again, so this was a sufficient criteria, so we know if it's fulfilled, then we will meet the deadline, but it was not strictly necessary. So we will give an example of that. So here we have 3 different tasks, and utilization is 50% for task A, 25% for task B, and 25% for task C. So the combined utilization is 100%, which is above the threshold that we computed with the Liu-Leyland criteria, which was 78%. But if we start to construct the schedule here, we are a bit lucky, because we will see here, if we start with task C, so it will execute, then when it's done, task B will execute, and then task A will execute, and then task B will execute again. And at this point, everything will repeat itself. And actually, we will meet all the deadlines here. So we were lucky here with how the periods were chosen and the computation time. So we actually, even though the total utilization was larger than 78%, we could meet all the deadlines. So that's why we said the criteria was sufficient, but not necessary. So if the total utilization is larger than 78%, we don't know. We need to do a detailed scheduling analysis to know if we will meet the deadlines or not. Okay, so what is the problem here? Yeah, so it's not an exact criteria. It is an easy criteria to compute, but it's not exact. So we can have these examples here. It's also not very general, in the sense that it only worked if the deadline was equal to the period, which it might not be. It also had another problem, and that is that you were not allowed to have any interaction between the tasks in form of locks. So you can't have semaphores, for example, that you quite often have to protect against data races and similar things. But it is very easy to compute this criteria. You just compute the total utilization and compare with the number. So it's said to be sufficient, but not necessary. So I think what we will do now is to try to deal with some of these problems. So we will actually compute the response time for each task. So remember again that if we take this example, so the response time is the time from a task is released until it's finished. And if we have a deadline now, we would like the response time to be less than the deadline, right? Because then we have a feasible schedule. So what we will do is that we will try to come up with an algorithm that will compute the response time for every task here. And then we will just compare it with the deadline. And if the response time is less than the deadline, then okay, everything is fine. So this will be an exact criteria. But this analysis will also be done under the assumption that you have no locks between the different tasks. Yeah. So I think we take the break now, and then we start this analysis after the break. Okay. Should we start? Yeah. So what we'll do now is that we will compute the response time, meaning the time between the task is released until it's finished, for every task. And then basically we will compare the response time to the deadline. And now the deadline can be equal to the period, but it can also be a tighter deadline. And basically we know that the response time will be the computation time for the task plus the time where higher priority tasks are executing, when they are preempting this task. So we need to figure out I here. So that's the trick. How can we compute that? And what we will do is that for each task, there might be a higher priority task, J. So the current task is I, and higher priority tasks are J. We'll execute a number of different times. So let's say we have computed the response time for task I. So now we have Ri. And then we know that the period for a higher priority task is Tj. In this case, if we look at the ratio here, this will be the number of times. So for every time we compute I, we will be interrupted a number of times by higher priority tasks. So, and if we take the roof here, or the ceiling function of this, so it means that this will be the smallest integer that is larger than this ratio here. So the ceiling of 1/3 is 1, let's say. So this will be, this number here will be the number of releases of task J while executing task I. Right? And every time task J would like to execute, it will take Cj amount of time. Okay, so this we can now use to create this formula. So let's say we have a guess of the response time for task A. So it will be the computation time for task I plus, and then for every task that has higher priority than task I, we will compute how many times will task J execute while executing task I, and then multiply that with how much time will it take each time, right? Because now we will get the new estimate of the response time. So it should actually say Ri plus here. So we start with some bound or some guess on Ri, and then we update this formula. And then we might get a higher value here. Then we insert it again, and then we might get a larger number here until we will reach a fixed point. So where we have a guess, and we'll get back the same guess. So what we do is that we form this recurrence relation. So it's exactly what we have above here. And then these set of values, when they increase, so this sequence here is monotonically non-decreasing. So we will always get the same value or a higher value. And then when we have reached the fixed point here, so we get the same value after executing this as we had before, then a solution has been found.
We shouldn't be overshooting. Then we will get a wrong answer. Like if we think about R supposed to be around 10 cycles, then you say, oh, let's put R 20, then it's not going to be a realistic solution.
No, so we have to initialize it. So we initialize it with C. That's a possibility. So you know that the response time can never be less than the computation time. So I think it will, so yeah. We start with a simple example here. So we have 3 different tasks, A, B, and C. We see here that we have assigned a priority to them. So in this algorithm, we can have assigned the priority using any strategy. It doesn't have to be rate monotonic. We just have a priority. And in this case, task or process A has the highest priority. So when we are the highest priority, what will be the response time?
Same as your computational time.
It's the same as the computation time, because there is no other process that can preempt you, right? So as soon as you would like to start to execute, you will also get access to the processor, and you will continue to execute until you're done. So for the highest priority process, the response time is equal to the computation time. So that's why RA is equal to 3. Okay, so we start with the highest, the process with the highest priority. Then we continue on to try to compute the response time for the process with the second highest priority. So in this case, that will be task B, right? And the computation time is 3. So we start with that as a guess. So it can never be less than that. Okay, so we initialize it, and then we run through this formula. And in this case, J will be all, or this HPI will be all the processes, the set of processes with higher priority than task I. So I is in this case B. So it's only process A that has higher priority. So we now take this formula. We start with our initial guess. And then we say, okay, if it now takes 3 time units to complete this task, and we know that the period of task A, which has higher priority, is equal to 7, it means that we can now be interrupted 1 time by task A. And that time it will take 3 time units. So this 3 here. Okay, so now we get a new guess on the response time. So it will be 6. So we got a larger number. Now we have to plug in 6 again. So we will replace 3 here with 6. And do this formula again, and we will get back 6 again. Right? So now we have reached a fixed point, and we know that the response time for task B will be 6 time units. Okay, so now we continue with task C, which is the task with the lowest priority. And the computation time here was 5, so we initialize our guess with 5. And then we now have to HP here, processes with higher priority. It will be both task A and task B. Okay, so how many times can we be preempted by task A in this case? So the period was for task A was 7, right? And if our guess for response time for task C was 5, we can be interrupted 1 time, or preempted 1 time, and it will take 3 time units. And we can also be preempted by task B in this case. So and the period here was 12 seconds, so it means that we can be preempted once. And each time it will take 3 time units. So that it will give us back 11. Okay, now we have to redo this again, because now our guess is worse than what we started with. So we plug in 11, where we had 5 up here. The problem now is that, suddenly something happened here, that now we can, if the time the response time will be 11 time units, then we might actually be preempted twice by task A. And it's still 1 time by task B, but now the response time is 14. We plug it in again, and then suddenly we might be preempted twice by task B as well. And then the total time will be 17, the total response time will be 17. And now it can be 3 times for task A, and 2 times by task B, and the total time will be 20. And now, finally, if you plug in 20 again, we will get back 20. So we have reached the fixed point. So the response time for task C will be 20 time units. Okay. So we got response time for task A will be 3 time units, for task B it will be 6 time units, and for task C it will be 20 time units. And now we can just go back and compare this response time to the deadline. Is the response time that we have calculated less than the deadline? Okay, then we meet all the deadlines. If it's not, we also have, we will not meet the deadlines for sure. So this is an exact, so this is a necessary and sufficient criteria. So sufficient and necessary. And if this fails, there will be a miss in its deadline. So this is, of course, under the assumption that the actual computation time, so this is a guess of the computation time, which is a problem on itself for how to compute. And the computation time might differ from iteration to iteration. For example, let's say you implement an MPC algorithm, then you solve an optimization problem while you're running, and the time to solve this optimization problem might be different from execution to execution. So you have to have a conservative guess here. But under the assumption that the actual time will actually take this number, then you know that you will miss its deadline. But if the actual time will be lower than this, you might or might not meet the deadlines. Okay, so since this is an exact analysis, you can do this for any deadline, which is fine. But we will go back now to an extension of the rate monotonic principle. Remember again, with the rate monotonic, we assigned priorities depending on the deadline, and we set the priorities based on the period. And under the assumption that the deadline is equal to the period, this way of setting the priorities is optimal. But if the deadline is less than the period, if you have a shorter deadline and you will set a higher priority, then if you set the priorities in this way, then this is an optimal way of doing it, optimal in the same sense as rate monotonic scheduling was optimal. So in terms of feasibility. So if there is a static way of assigning priorities that will meet its deadline, you will find it by setting the priorities in this way. So just to say that you don't have to set the priorities on the periods. You can set them on the deadlines as well if you have other deadlines. But then to know if you will meet the deadlines or not, you have to do some more fancy analysis. For example, this exact analysis where you compute the actual response time. Okay, so this was all about the static scheduling. So I started by saying that we will also look into where you have dynamic scheduling, and we will talk about one such principle where you will have deadlines. And so this is called earliest deadline first. So this principle is based on the idea that you always choose the task with the closest deadline for execution. And it has some, under the assumption that you have periodic processes with deadline equal to the period, if the total utilization is less than 1, so meaning that if you use the processor less than 100% of the time, then you will actually meet all the deadlines. Okay? So compare this to the criteria we had before, the Liu-Leyland criteria, for the rate when you had the fixed priorities. So then you had this bound that it should be less than 69% if the n was very large, right? So that means that you will not use the processor for 31% of the time. If you would like to know that you are guaranteed to meet the deadlines. But if you have a more fancy scheduler where you have these deadlines instead, then you can use the processor up to 100% of the time. So that's an advantage. So compared to fixed priority scheduling, you can support higher utilization and still meets all the deadline. The drawback, of course, is that you will have fixed priority scheduling is easier to implement as the priorities are static. And here you need to change the priorities depending on how close to a deadline you are. So it's a more complex system to implement. And if this makes sense or not depends on if you have natural deadlines that you would like to meet. So if you have deadlines, then in some sense it would make sense for you to just tell the operating system what are the deadlines. But if you do not really have the deadlines, then it might just be better to use these priorities to say, okay, this is, for example, based on the periods that you have. So you assign the priorities based on the periods. A drawback with this is that if you run into situations where you can't meet the deadlines, then the fixed priority scheduling is a little bit more predictable, in the sense that the operating system will always follow these priorities. So higher priorities will always execute before lower priority tasks. But if you have this earliest deadline first strategy and you miss a deadline, then you will miss the deadline for the next task as well. So it will continue on like that. So you will have a domino effect of missed deadlines. Which is not something you get with the fixed priority scheduling. So there are some operating systems that supports this earliest deadline first strategy, but most of the ones that you have, the commercial ones, and also like in FreeRTOS, only support rate monotonic scheduling. And if you would like to change, you can, for example, in FreeRTOS, you can yourself change the priority of different processes or tasks while executing. But there is no built-in support for posting these deadlines and have the scheduler do it automatically for you. An advantage with earliest deadline first is, of course, if you can't meet your deadlines, so the rate monotonic scheduling can completely block lower priority tasks from execution, right? So let's say you have a high priority task that will just consume all the processing time. So the other task will not have a chance at all to execute, which is not the situation when you have the earliest deadline first, when the priority will change dynamically depending on the deadline. So there are strengths or pros and cons with each method, but it's good to know about what are the pros with rate monotonic scheduling and what are the pros and cons with earliest deadline first. Earliest deadline first has another advantage, and that is that you will have fewer preemptions in practice. So we will have fewer context switches, and we will see no, we will not. I don't have that example, but this is the case, of course, because you will, when a task is scheduled, you have the deadline in sight, right, and then you execute until you're done. Then another task will continue to execute. Okay, so that was all about earliest deadline first and fixed priority rate monotonic scheduling. So these are typical exam questions. And there is no reason for not solving them, because they are very straightforward. But we will see a little bit about how can we take advantage of these strategies that we have talked about now for our control applications. And so if you go out and start work at some automotive company, maybe, so you will see that there are the control group and then there is the software group. And today it's still pretty much the case that you have the control people, they will design the controllers, they will do everything in MATLAB, and then when they are done they will throw everything over some wall to some software guys, and they are responsible for implementing this. So this, I would say that this was actually the case if you go back 10 years. So with the tools becoming more fancy, and you can do code generation and so on, so also the code, or the control guys, they actually have a larger and larger responsibility for also for the software design. But if we look at these analysis, so what we talked about now, the fixed priority, earliest deadline first, and so on, all these techniques and real-time operating system, they were from the software community. So those people that came up with this, they were not control engineers. And if you talk to control engineers, I mean, going back in the linear control system design, you basically assume that, okay, I have unlimited access to the processor, right? You don't take these limitations into account, that you might be sharing the processor with a lot of other control tasks. And that's not included in your control design at all. But as we have, as you know now, that this will affect each other, because if you have other tasks, then the response time will change, and longer response times will mean that there are more phase delay introduced, and phase delays are bad for stability and so forth. So you might have new problems. So the control engineers, they say that they don't really care about the implementations. They say just buy a fast computer. And the software engineering guys, they say that, okay, they don't really understand the control timing that you have. And they say that you have hard deadlines, but we just argue that you have firm deadlines and so on. So what I'm trying to say here is that the control field and the scheduling field, they have evolved as separate subjects for many, many years. And what we try to do in this course, since you are mainly control engineers, I think it's fair to say, to teach you a little bit about what's going on under the hood in the real-time operating system. It's relatively easy to understand what's going on, so it's much easier for you to understand the basics of a real-time operating system than it is to teach the software guys everything about control theory. So we will go back and discuss the typical assumptions. So in control theory, you have a model. So you have of a task. You assume you have a fixed period. You have a known worst case execution time, and you have a deadline that is equal to the period. So this is what a control task is viewed from those guys that built up the scheduling theory. So, but when we start to think about this, does we always have a fixed period, for example? And sometimes you have a fixed period, sometimes you do not. You could have, for example, a controller that is not sampled against time. So if you have a combustion engine controller, you would like to compute your controller based on the angle of the crankshaft. Is that the word? Instead. So the angle will decide when to do the sample. You could have different modes in your controllers. You could have hybrid controllers. You switch between different modes, and then you switch mode depending on state conditions, etc. You could have control tasks that are triggered sporadically by sporadically arriving measurements over the networks. And you could have control tasks that should be executed when a button is pressed, for example. So the button is an external generated event. You don't know when it will happen. It's just you should do something when it happens. Another possibility is that you, for example, to save energy. So if you have a controller running on battery, it could be an advantage to try to have a slow sampling period when not much is happening in the process, and then when the process spins up, you start to have shorter sample times. So then you could have it, so the sample time can be online adjusted by a high-level scheduler. So this is another case where you will not have a fixed period. So this assumption does not always hold. The next assumption that we had was the worst case execution time. So it needs to be fixed and it needs to be known. And the problem with the worst case execution time is that it's a very, very hard problem these days. And if you're now running a controller on the processor, just assume that we will do the same calculations every time. So it might, even in that case, it might be problematic to compute the worst case execution time, because there is a lot of caching mechanism going on inside the processor. So if you have taking a computer engineering course, you know that there are pipelines, etc., and you have quite complicated memory structure with different levels of memory of different speed and so forth. So when something is in the cache, it will go, the computation will be much faster than if it's not in the cache, etc. So you can't just run the code once and take some measurement and say, okay, this is how much it will take. So it's more complicated than that. So basically you will only get estimates or guesses on this worst case execution time. Yeah, and another thing I had in mind was that you could also have logic inside your controllers, right? So you have if statements. So if some condition is fulfilled, you will do this. If something else, you will do that, right? So then, depending on if this condition is fulfilled or not, you will do different tasks, and they might take different amounts of time. And if you have a lot of if statements, then you have a lot of different combinations that you need to take into account while doing this analysis. So this is a whole problem on its own to come up with these. And then, of course, if we go into control-specific situations. So for those of you that took the Model Predictive Control course, you know that you could have, you always have this trade-off between doing longer execution time, doing better on your optimization, you will get higher quality control, or if you do a little bit worse on the optimization, but you save time instead. So this is always a trade-off. Okay, so the conclusion is that the worst case execution time is complicated. And then, do we have hard deadlines? So for these type of control problems, as we discussed before, the deadlines are often firm rather than hard. So it's okay to miss a few outputs. The world will not end if you do that. But we don't want to do it too many times. And of course, what you can allow or not depends on the process itself. So for example, in unstable processes, it's much worse to miss deadlines than if the process itself is stable. And if you miss a deadline, if you think in terms of controllers, it's usually better to complete calculating the control output after the deadline than not computing the control output at all, right? Because if you don't compute it at all, then the process is, or the controller is running in open loop, basically. But if you compute it a little bit late, we might have degraded performance, but still it's not open loop. So we don't want to have situations where the task is aborted if we miss the deadline. And when it comes to deadline or stability analysis, depending on how sophisticated the analysis is, but guaranteeing this, that you meet the deadline, if the deadline is equal to the period, does not by itself mean that the closed loop system will be stable, right? So of course you could take this into account. You can think about this as a delay. So when you design your controller, you will have a certain phase margin to take into account that there might be a delay, and then you make it large enough so you know that it will be stable even if you see this as a delay in the control loop. And then other aspects that we have is that, for example, the inputs and outputs. It's not really clear from the analysis, when are we reading the inputs? Is it at the beginning of the period when the task is released? Or are we reading the inputs when the task starts to execute, for example? So this will also affect the control performance. And the same thing for the outputs. When do we actually send out the control signals? Is it when we're done with the calculation, or when the task finishes, or at the end of the periods? So this is all affect the control performance, but it's not really taken into account into the analysis. So we will look into this. And here we have a periodic task running. And we see here that this is where the task is released for period k minus 1, and this is when it's released for at time, or at instant k and instant k plus 1. And one thing we can notice here is that here we will have other processes with higher priorities. So the response time will be different from the computation time. So here we are, some other process with higher priority are executing. And notice here that the time, or the response time, will be different for every k here. Or it might be different, because it depends on what other tasks would like to execute. So we can then introduce the jitter and the sampling jitter and the input-output jitter of task I. And we can talk about the latency of job K, of task I. So the sampling latency here is this time. So the time between the task is released until the task starts to execute here. So we see that it's different for every occurrence of this control task. And the input-output latency is the time from when it has read the inputs until it's actually send the outputs. So here. And then we have these two forms of latencies, and then we can talk about how much the latency differs. So the sampling latency and the input-output latency. So that is the maximum So the sampling jitter is the maximum latency minus the minimum latency. So it's the spread. And the same for the input-output jitter here. So what we would like to have, of course, is that we would like to have a low sampling latency and a low input-output latency. And we would like the jitter to be as low as possible as well. Because the latency and jitter will make the analysis of the closed-loop behavior very complicated. And basically there are no good analytical tools to take this into account in the analysis. So you have to rely on simulation to simulate all the different control tasks that you have and see how it behaves. There are some results, but they are conservative results that you can use here. So, but this is basically an art how to do this. But we will look at one possible way of reducing the latency and jitter. And this is a control task, so it's written at a very high level. So basically the control task will read its input, then it will calculate the output, and then it will write the output to the process, and then it will do some update of its states. So what we would like to do is to divide this control task into two separate tasks. One where you do this, read the input, calculate the output, write the output. That is a high priority task. And then you have this update state where you will do other things. We will look into what you actually do here and keep this as a low priority task. So this is a PID controller. So you read the inputs here, and then you calculate the proportional part, you calculate the derivative part, and then you calculate the output as the proportional plus integral plus derivative part. And then you have some actuator saturation here that you might or might not include in the control algorithm, and then you send out the output. But this is the first part of the algorithm, and the second here is the update state, where you update the integral part. And that you can do after you have calculated the output. Right? So this is something you only need to do before the next time you run the controller. Okay, so if we now divide this control task into two parts, so we will have this first part here as a high priority task, and we will have this as the low priority task. So what is the deadline of this? So doing the update state, that needs to be done before we execute this the next time, right? So the deadline for doing this is the period of the task. And the deadline for doing this, you would like to keep as short as possible, right? The shorter the better, basically. So if we now, instead of treating it as one big task, we divide it into two different tasks. So this is calculate output, and this is update state. So the calculate output should have a short deadline as possible, and the update state should have a deadline that is equal to the period. So what we will do now is that we will look at an algorithm that will try to assign priorities to these tasks based on the deadline monotonic principle that we discussed previously. So the algorithm is not very complicated. but we have to run it in several iterations to reach a fixed point. So what we will do is that we will start by assigning initial deadlines. So the initial deadline for update state is equal to the period, and the initial deadline to the calculate output, which is the high priority, is equal to the period minus the time to calculate the update state, right? Because in every sample you need to do both of these, right? And then what we do is that we assign deadline monotonic priorities to all subtasks. Remember again that if you assigned priorities according to this principle, it means that the shorter deadline will have a higher priority. Okay, so we assign priorities in this way, and then we do the calculate the response time the way we did previously here. We calculate the exact response time for all tasks. Okay, and then we get a new response time for the calculate output, and then we set this as the deadline again. So we'll have a new deadline. So it means that the deadline might be tighter, right? So and then we repeat here again. So then we reassign the priorities with the new deadlines. So it means that the relative priorities of the task can change now. Because if you got a shorter response time, then you get a tighter deadline, and the task will have a higher priority. And then you calculate the response time again, and then you reassign the priorities like this until you reach a fixed point. So we will see with an example here. So we have, in this case, we have 3 different cards. And in this case, it's basically an inverted pendulum here. And they are controlled by one processor with a real-time operating system. We have, and the length of the pendulum is different. So we see here that we will have faster dynamics here with a shorter pendulum than if we have a long pendulum. But yeah, so the plant dynamics is different. So we will have different, we design controllers in the same way, but we will have different periods now, because we will have a shorter period for the faster dynamics than we will have for the longer dynamics. So we will not go into the design of the controllers here. We just say that all the controllers, if they were executing alone on the processor, then they would have no problem stabilizing the pendulum. But if we now if we simulate this system, so now we assume that controllers are all sharing the same processor. Pendulum 1, which was the pendulum with the fastest dynamics, and then the shorter periods will have highest priority. So whenever it would like to execute, it can execute its control task. So if we start with a small deviation in the angle here, it will actually stabilize, so we will go back to equilibrium here when it's pointing upwards. If we go for the second pendulum, the problem now with the second pendulum is that whenever pendulum 1, it will have higher priority, so it would start to execute. So this can be preempted. So but still in this case, if we simulate it, it will manage to stabilize it. But for pendulum 3, that worked if it was using the processor alone, it can now be preempted by both pendulum 2 and pendulum 1. And then we see here that things go really bad. So it does not, that controller does not really work. So this is a simulation under rate monotonic scheduling where we have the task 1, 2, and 3. And we see here, so this is when it's up here, that means that task 1 is executing, and here it's blocked. And we see for task 1, it always gets access to the processor when it wants. But that's not the case for task 3, and this is the reason why things went bad. So I will try to wrap up here. But if you now run the algorithm that I just introduced before, so we divide the control task into the calculate output and the update state, and we assume that the time will look like this. Run through the algorithm, so we will have 6 tasks now instead of 3. And until this will converge, then we will see here that the calculate output time for task 1 will be 1.5, and for task 2 it will be 3.0, and for task 3 it will be 4.5. So this is the new worst case input-output latencies that we have. And by doing this, so but basically by separating the control task into every task into 2 different tasks that you schedule separately, so the same control design will now work fine also for pendulum 3. So this was just an example of that. Here you can, if you know a little about scheduling, you know a little bit about control design, then you can take advantage of that to do a better implementation as well. So with that, we end this part. I'm sorry for being a few minutes late today.